Okay, just this will be recorded. Let me introduce our speaker today. It's Christoph Dürr. He graduated in 1996 from the University of Paris South on quantum cellular. His work was on quantum cellular automata. He has worked mainly in discrete tomography, algorithmic game theory, scheduling, and online algorithm. Today, he's a senior researcher at CNRS and usually at Sorbonne University, but we have the pleasure of having him in Chile for this year. Is it this year? This year at the Universidad de Chile at the Center for Mathematical Modeling, CMM. So let's give him an applause.
Hello, everyone. I will talk about explorable uncertainty. So you know, usually in a combinatorial optimization problem, you have a very well-defined instance on which you have to compute the solution. But sometimes in real life, sometimes this instance, this data is actually hard to get. And so this gives the motivation to study models where the data is uncertain. And there have been several approaches to this difficulty. And this difficulty here, and so in this model here, we study a model where we can actually make queries and get the real data. And the goal is to, you know, make these queries the most efficiently possible. So let me first introduce an adversarial setting. I will explain the word adversarial in a second. So suppose, start with an example. So we want the cheapest option out of several options. Suppose an option is a value, but you don't know this value exactly. You only have a rough bound. You have a lower bound and upper bound. Here, for example, for the option U, I know that it lies between in this interval. And for the option V, I know that it lies in this interval, but I don't know the exact value. And I want to find the cheapest of it. So I can do a query for a given option that will reveal me the exact value. And I have to make queries adaptively, so in the sense that once I did the query, I can decide from the outcome what will be the next query, until I have enough information to solve the problem. And in the uniform query cost model, I just want to minimize the number of queries. And the examples, I will just consider that. But in general, there will be a query cost for each option. I call it option in this example, but it will be a variable or weight of an edge in a graph, something like that. And you want to minimize the minimum. So let's look at this example. What could be a query V? For example, I mean, there are just two kinds of algorithms for this example. It's very simple. So you could start to query the option U. And then, well, if you're unlucky, it turns out that the value of U actually falls into the interval of V. And then you still don't know which one of the two is the cheapest. And then in this example, then you would need to query V also. So in this example, actually, you cannot quite read it because it's all in gray. Let's make it a bit larger, maybe. Yeah. So, okay, I feel very old now.
No, you can just put down.
But then I still need to push it somewhere. Okay. So in this instance, you know, I made two queries, but in hindsight, I mean, on this instance, by instance, I mean the exact, like the vector of values for each option. On this instance, it would have been enough to query just U, V, right? Just by querying V, since it's to the right of the interval of U, I know that U is the cheapest one. Even without knowing what the value of U is, I know it's the cheapest. So in hindsight, I could have solved the problem with a single query, but I made two queries. So this ratio, 2/1, is the competitive ratio of this scenario. And if I query V first, the same, like a similar thing could happen. And if I query V first and the value falls into the interval of U, I need to query U as well. But here it would have been enough to query U only. So in this scenario, also the ratio is like 2/1. And this already tells you what my performance measure is. We call it the competitive ratio. It's like an approximation ratio, but where we compare the performance of an algorithm with an optimum. But we don't call it approximation ratio, but competitive ratio, because we borrowed the terminology from an area called online algorithms. There's nothing online here, but it's a problem with hidden information. So somehow it has a similar flavor. We just borrowed the terminology. So what we do here is that, for a given problem instance, in this example, that will be the vector of the exact values. Algorithm of J, instance J, would be the number of queries made by this specific algorithm of J. And this cost we normalize by dividing by opt J, and opt J is the minimum number of queries of J. So there is something a bit subtle. And so this ratio maximized over all J is called the competitive ratio of this algorithm. So this is the measure of the quality of an algorithm. And now we would like, for example, to have an algorithm that has the smallest possible competitive ratio. And if we can find a matching lower bound, a lower bound would be an example like the one on the right, then we will, in terms of competitive ratio, we found the best algorithm. So this is the framework in which we are studying this kind of problems. And there's something a bit subtle to say about opt of J. So this is the minimum set of queries you need to do for the instance J. But this set of queries you could compute if you know J, but you still need to make the queries to prove to someone else that, okay, this is the minimum. Okay, so opt J is a bit more powerful than an algorithm in this term. It's not a decision tree. It really depends on the instance. So it's a sort of ratio. This ratio sort of measures the price of this hidden information, if you want. And so this setting has been studied for several problems that are summarized in this table here. So this lower bound that I gave here of 2 on the problem where you want to find the minimum in a set. This has been introduced by Kahan in 1991, 30 years ago. And to find the minimum in a set, the lower bound is 2, and actually there's an algorithm that reaches the value 2. So this table here is the lower and upper bound on the competitive ratio for various problems with these references. And lower bound is a construction like this one, like an adversarial construction. Given an algorithm, I try to build an instance that will fool every algorithm. So this is actually easy in that sense. The lower bound to find, and an upper bound would be a specific algorithm. And you see that for many of these problems, the lower and the upper bound, they actually match. So these problems are well understood. This adversarial setting is well understood. So by geometric problems, we mean something like finding the convex hull of a set of points where every point is in an uncertain region, for example, or minimum spanning tree. You need to figure out identify a minimum spanning tree in a graph where you don't know the edge, where this kind of problems. And here this constant D is like the size of a set. Cheapest set is you want to identify the cheapest set, and the price of a set is the sum of the values it contains, and these values are uncertain. So this kind of problems are known. So since this is well understood, now we move to a stochastic setting. A stochastic setting is also interesting because we deal with an adversary that is a bit less aggressive. I mean, here so why are we using the word adversary? Because we can see this ratio as the value of a game played between an algorithm and an adversary. The adversary will reveal the values and will try to get this ratio as high as possible, and the algorithm wants to get as low as possible. So it's a game played between an algorithm and adversary. And in the stochastic setting, we consider an adversary that is a bit less powerful. The idea is that maybe in real life, the instances are not just there to make you perform bad. Maybe the instances follow some stochastic rules. Maybe we have some stochastic model on the instance, and then it should be a bit maybe more realistic if we know the distributions. But this is the model we consider. And this leads us to the next slide. So the stochastic setting is the following. Now, every value, that was the value of an option before, the value W sub V, where V is the value, like the variable, it is drawn according to a distribution. So we still have an interval with a left endpoint LV and a right endpoint RV. But on this interval, we have a distribution DV. And the value is drawn according to the distribution. So you, as an algorithm, you know the interval and you know the distribution. But the value you only know when you query it. Okay. And in this setting now, the performance of an algorithm becomes a random variable because it depends on these random values. So an instance here, J is now the vector of distributions. And the expectation here, the number of the query cost, is taken according to the values drawn according to these distributions. And we compare it with the expected odds. So this is the measure we take here. You could also say that we would like to minimize the expectation of the ratio. This would be another approach, but it's more difficult, in fact, in general. And so usually we consider that.
But in particular, sorry, can I?
Yes.
In particular, the distributions could be just deltas, right?
Yeah. So
why is this like different?
Once again.
Like if I understood correctly, then now J is a vector of distributions.
Yeah.
Right. And these distributions could be just have all the mass in one point.
It could be, but then there is no uncertainty, right?
Then you collapse the previous block.
No, I cannot, because in the previous work, the value is chosen by an adversary, and there is no probability associated to it. So, whereas here we have a distribution, and you will see in a second, I don't need much information about this distribution. In fact, these left and right endpoints of the intervals, they divide the scale of the values into small portions. And in fact, I only need to know the probability inside each portion. So I don't need the full distribution. I only need some information. Also, for some technical reasons, there should be no point-wise probability mass on the extreme values of the intervals. It's like this interval should be open in some sense. But this is too technical. Yeah. Oh, also, I need to step a bit back. Okay, I step back. You can stay seated where you are. The idea is that there's another model that people have studied in the literature, where they also have a stochastic model, but they study combinatorial optimization problems where you have to come up with a solution, but every item in your solution must be a queried item. For example, there's this classic standard model of stochastic knapsack, And the items, you don't know the exact size, but when you take it, you have to query it, and then you know the exact size. And only and you need this to be sure that your budget won't be exceeded. Certainty. And this is quite a different setting. In this setting, you know, we have to identify the minimum, but we don't necessarily need to know what the minimum is. So this is quite different, and this model has been less studied. And this stochastic model, yeah. So one important work is the work by Shaplik, Halderson, De Lima, and Tonoyan from 2020, and they studied the following two problems. So one is sorting n values. So instead of having like two values and knowing which is the minimum, you just want to put them in order. And you know, once you identified a value and you know that it's larger than a whole set of other values and smaller than its complement, then you immediately divided the problem into two independent subproblems, right? So this gives the idea that there's a dynamic program approach here, and they managed in time n to the 6 to compute the optimal decision tree. So they identified the optimal algorithm. So they don't give the competitive ratio, but by the way they construct, we know that it's optimal. It's the best algorithm.
It's the best competitive ratio.
Yes. And for finding the minimum, it's open whether this optimal decision tree can be computed in polynomial time. Could be NP hard, could be polynomial, people don't know. And I don't recommend you to think about this problem. I tried like a month, so it's really difficult. But they have a randomized algorithm that has, yeah, this is almost like the competitive ratio, 1.5 competitive ratios. Okay. But there's an interesting observation about finding the minimum. Let me, and this is illustrated here. Let me zoom on this. This is very interesting. So I want to find the minimum over, let's say, these four values. And let's order these four values according to the left endpoint of the uncertainty interval. There are only, in fact, there are only two kinds of feasible query sets. I mean, query sets that are necessary in order to identify the minimum. So one such query set can be obtained by querying these intervals in the order of the left endpoint. So I query first this one here, I get this value, then I query this one here, I get this value. Now I still don't know which one is the minimum because this falls into that interval. So I query this one as well. And then I know which one is the minimum because the minimum of the queried values so far, it is to the left of all the unqueried intervals. So I don't need to query them anymore. So now I'm done. So here with three queries, I identified the minimum. So this is one kind of feasible query set. And another one would be to query all the values, here on the right, to query all the values except the value x that minimizes the left endpoint, but provided that all these answers to the queries are to the right of x, to the right. And if that is the case, then this is also proof that x is the minimum. So these are the two kind of possible optimal query sets. And yeah, this will be used this can be used in an algorithm where yeah, you can kind of try to query these elements in this order, and at some moment you decide no, you want to produce a witness set of this form. But I don't want to detail into this algorithm, but this is some interesting observation. Okay, finally, now I can tell you what we did. What is the problem that we studied? We want to orient a graph. So this somehow generalizes sorting, which would be like orienting the complete graph. The idea is that I don't want to compare all pairs of values. I just want for some values to know which one is the smallest. And these pairs of values are connected by an edge. And somehow I want to orient the edge from the largest to the smallest value. That's the idea. And I want to, and I want again to minimize the query costs for this. And we also consider a generalization of that where instead of a graph, we have a hypergraph. So if you don't know what it is, it's just, I have a collection of sets over a universe of variables. And in each of these sets, I want to identify the minimum. So this problem generalizes both finding the minimum and sorting. So we studied that problem, and to be honest, I don't have a real motivation for the problem. I can come up with a motivation but it will be a fake one. But just we studied it. I mean, it's a network problem. And this has been presented last year in ESA, and the authors are Evripede Barnbis, myself, Thomas Erlebach, Murilo de Lima, Nicole Megov, and Jens Schlöter. And in fact, Jens Schlöter, the student, he did most of the work. But he's very brilliant. So if you see a postdoc application of him, I recommend that you hire him, because he's really, I mean, I wish I had a student like this. Yes.
So when are you satisfied with the part? Is when you know what?
So for this oriented graph, I would be satisfied once I know for every edge which of the endpoints is the smallest.
Oh, okay.
Yeah, I don't need to know the value of the smallest, but I need to know which is the smallest. Yeah. All right. If you need some motivation, I mean, this kind of queries, I think in the industry, they appear all the time. You know, companies, they make market studies to, in order to figure out real values, how many customers will buy this stupid cell phone, and, you know, or this kind of things. Or you're a city and you have to decide where to put schools. You have to figure out really how many children are in this barrio. And I mean, this happens all the time. Okay, so let's work through an example before telling you in detail what we did. So we want to orient the graph, and let's orient the bipedal graph. Let's look at a very simple bipedal graph. We have three vertices, x, y, and z. And these are the uncertainty intervals of x, y, and z. And these are the probabilities. So the value of x is within this part of the interval is probability 1/2, and in this part is probability 1/2. And epsilon is an arbitrarily small constant, but it's not 0. So this is important. Oh yeah, and forget about these p values that they shouldn't be here. So I claim for this instance, opt, the expected value of opt is about 1.5. So let's look at the variable x. With probability 1/2, it's in the first part here, and then it's enough to query just x. So with probability 1/2, opt just needs to pay one query. And with probability 1/2 times 1 minus epsilon squared, x is here and y and z are here, and then it would be enough to query y and z, right? So with probability 1/2, opt would just pay 2, and then with a very negligible probability, he needs to query all three variables. So when epsilon is small, roughly this is 1.5, and an algorithm needs to, I claim it needs to query 2. So if you start, as an algorithm, if you start to query x, then what is the decision tree? With probability 1/2, you're done. And with probability 1/2, well, you need to query y and z as well, because they have because x falls into their interval, and then there's a non-zero probability that x and y are actually smaller. You need to query them as well. So in this decision tree, the expected cost is exactly 2. But if you start to query, let's say y, then with a big probability, you need to query z as well. And with a big probability, you will be done. And with small probabilities, there will be another part of the decision tree, but if you look at already at this branch, that is the dominant branch, then the cost is 2. So roughly this is 2 and the ratio is 4 sort. And in fact, we have an algorithm that I don't show you that reaches this ratio. And this algorithm also works for orienting a single hyper-edge. That means, but only for uniform cost. That means identifying the minimum in a single set. That's what I mean. Okay. Now, finally, let me go to the final slide and tell you what we really do. Yes, and before that, I need to. Okay. Let's look at an example again. Suppose we have an edge between 2 vertices u and v, and we want to orient that edge. We want to know whether u or v are smaller. Look at the uncertain intervals of u and v. If there are disjoint, you know immediately, without querying, which one is the smallest. So you can just pretend that these edges don't exist. Okay. So now if they overlap, well, you know that you need to query one. So let's say you query u, and then if this value u falls into the interval of v, then you need to query v as well, right? Okay, so by looking at this example, what we know is that every vertex has a probability that it needs to be queried. We call it mandatory. And this probability is just the probability that related variables have their value in this interval, because then you need to query it as well. And this is something you can easily express. So every vertex has a probability that it needs to be queried. And another observation is that if the intervals intersect, then you know that you need to query at least one of the two, right? So you know that at the end, the query, the set of variables that you query form a vertex cover of your graph. So this is important. So, okay, maybe you don't know what vertex cover is. I'll explain you in a second. So this is all you need to know today about vertex cover. So it's a standard problem in combinatorial optimization. You're given a graph on vertex set V and edge V, and you have costs on the vertices, and you want to find the cheapest set with respect to these costs, a set S. For example, these 3 yellow vertices here, they form S, with the property that every edge UV, at least one of the endpoints U or V must be in S. So we say that this edge is covered by S, and we need to cover all the edges, the cheapest one. So this problem is easy for bipartite graphs, but in general it's NP hard, but it can be approximated. And one way is to solve a linear program that is very easy. Every variable is associated to a vertex. It's 1 whether it's in S and 0 if it's not in S. And you remove the integrality constraint so you can solve the linear program. And the constraints are set, just says that for every edge, the sum of the endpoints has to be at least 1. No? That's very easy linear program. And this has the property that it's half integral in the sense that every extreme point solution or the vertices of the polytope defined by this linear program have the values in 0, 1/2, or 1. And then if you round it to 1, you get the 2 approximations. That's very easy. Okay. So before telling you what algorithm we came up with, what do we want to do? We want to design an algorithm that has a good competitive ratio. So we need to compare with opt. So we need an expression for opt. And this expression for opt should actually guide us to design an algorithm. And the expression for opt, what would it be? You can write like this. It's the sum. It's the sum over all set of vertices M like mandatory, of the probability that M is mandatory, that if you query M, then you can solve the problem. You can orient the edges times the cardinality of M because you query them. But then it's not enough, times the probability, the same probability P of M of the minimum vertex cover for the remaining graph. So remaining means that once you remove the M, you remember every solution is the vertex cover. So you also need to query this vertex cover here. Yeah, but you remember, querying a vertex cover might not be enough. Sometimes you need to query a vertex, another vertex as well. If this value falls into this interval, and this is taken part of in this first part of the expression. And I can write it differently. The first part I can write as the sum over all vertices of this probability PV that actually the vertex V individually is mandatory. Okay, now I need to design an algorithm that performs well with respect to this expression. So this tells us already two things. So if the probability of a vertex PV is big.
Sorry, Christoph.
Yes.
P of M is the sum of the probabilities that each vertex is mandatory. The sum over M.
Yeah. No, yeah. I can express it. I don't know if it's trivial, but I can express it like this.
My question: what is the definition of P of M?
P of M is the probability that a set of vertices is mandatory, and
that's exactly the set of vertices that
yes,
is mandatory.
and yeah, you need to query them, but they're also enough to solve the problem. So you don't need to query more than M, but you need to query M.
Okay.
So
that M is exactly the set of vertices, you know.
yeah. So op will produce a set. So op will produce. In fact, yeah, op will produce. Okay, maybe I didn't prepare enough, but I don't know how to explain better to you. Yeah.
The probability that this subset is required.
But this is without considering the ones in the vertex cover, because that's considered in the other part of the sum.
Yeah.
So at the end of the day, it's the probability that M plus the vertex cover is the optimal value.
Yes. Yes. Yeah. And because we work with expectation, we can separate those two parts. We have two expressions. And okay, so yeah. But the important thing for us now is that if for some vertex the PV value is big, then we can actually afford to query it, because then locally the ratio would be good, because opt already pays a lot for this vertex. And the other thing is that we don't want to actually we want a good vertex cover. We don't. But it's hard to compute the optimum, but we want good vertex cover. We don't want a very expensive vertex cover. Okay, and this led us to the following algorithm. So we call it the threshold algorithm. There's a threshold D that will be optimized. And first we compute for every vertex V the probability PV that V belongs to the feasible query set. This is kind of trivial for graphs. Then M like mandatory are vertices that have a big enough probability. Then we look at the graph where we remove M. And for this graph, we solve the linear program the vertex cover linear program. With what I told you before, the solution would be half integral. So this divides naturally the vertices into three parts: V0, V1 half, and V1. So V1, we want to carry them as well, but V1 half we don't know yet. So now we compute an alpha approximate vertex cover VC prime for the graph restricted to those vertices V1 half. And now we query in one batch, non-adaptively, the union of these three sets, M, V1, and VC prime. So once we query them, then we are not done yet, because depending on the value, there might be other vertices that we need to query as well. And these values and these other various values, we can query them again in one batch. And so this is an algorithm that has a very limited adaptivity. It is just doing two sets of queries. We could allow more adaptivity, but we don't know how to exploit this. And this is our algorithm. And so by analyzing it, comparing to the expression of opt, we figure out that the competitive ratio is some function f of alpha. And yeah, we optimize v. I don't tell you what it is. It depends also on f. And this f of alpha, it's some value between the golden ratio, 1.618, and 2. So when alpha is 1, it's actually the golden ratio, and when alpha is 2, it's just 2. So for example, on a biped graph, this algorithm performs very well, because then alpha is 1, and generally it's only 2. And we can generalize this to hypergraphs, but there's some difficulty. One difficulty is that it's actually difficult for hypergraphs to compute this probability PV. In fact, it's a sharp P hard problem. It means that we can only approximate this probability by sampling, and so this sampling gives some approximation in the value of PV. And as a consequence, the performance ratio is only between the golden ratio plus epsilon and 2. And this epsilon, like 1 over epsilon, turns into the running, gets into the running time of the algorithm. Depends, it defines the number of samples that you want. And also, this is only with a high probability, and this high probability also comes from the sampling.
And you don't need the plus epsilon in the, there's not 2 plus epsilon.
In the 2, no. And then and also for hypergraphs, this step is a bit more complicated, because there I cannot query these mandatory vertices in one batch. I need to query them, I might need to query them in several runs. So for example, if I were in this example here, I might need to query one vertex, another one, depending how the values come out. So for hypergraphs, actually, I need more adaptivity.
It's fine, no worries.
Yeah, and that's it. So this drawing here means that it's the end of the talk. And this drawing in France, so usually you have it in books at the beginning or the end of the book, and in France it's called cul de lampe, which means like the S of a lamp. So this testifies that French can be elegant and very vulgar. And that's the end of my talk now. I have to take questions.
So, any questions?
And yeah, you on Zoom, if you're still there, you can also ask. No, okay, Victor, if you want, you can ask questions as well.
I have some questions.
Yes.
Can you explain a little bit the intuition? Can you move the
Yes.
the intuition of this set of queries that you actually do? I mean, the ones that are mandatory, it's kind of intuitive that the optimum is paying enough for them, so you also don't lose too much,
Mhm,
right?
yeah, yeah.
But can you explain a little bit this B1 and BC prime? Like, what's the?
Yeah, I wish I had good intuition. So I know that, in fact, why are we doing this into these two steps? Why don't we compute immediately an alpha approximation for this graph here? That would be enough. I think if we do this, then we will still have V1 will be part of the alpha approximation, I think. But for the analysis, I think it's better to divide like this and to have distinct parts of our query set. There's another thing that I don't like so much here is that we're just focusing on the size of the vertex cover, but some vertex cover will generate more work in step 5 than another vertex cover. And we're not really taking this into account. So, and by the way, we're not sure that this is the best algorithm because we only have a lower bound of 1.5 for this class of algorithms. So there might be a place for improvement. But this is what we figured out. Yeah. So, but in general, I mean, I find this model very intriguing, very interesting. You can take any combinatorial optimization problem and apply it to it, but sometimes you get a new interesting problem, but sometimes it's trivial or something. It's not easy to get an interesting problem in this setting. This was my experience. Okay, but okay, let's finish now then.
Thank you very much.